Okay, we've been given the activity here of a sample of plutonium-238, and we have to plot the activity against time. Okay, so activity on the y-axis and time on the x-axis. The becquerel, by the way, make sure you know what that means. 1 becquerel means the decay of 1 atom of the sample per second. Okay? Right. So, activity on the y-axis. On your question sheet, the grid has given you 6 squares to play with on the y-axis and on the x-axis. So, activity goes up to 980. That's close to 1,000. Well, 5 goes into 1,000 well. So, it's going to be 1,000 there on the 5th one. Okay, that's the best scale to choose. So 0, 200, 400, 600, 800, 1,000. Okay, you must remember to label your axes. So that's activity. And give the unit. Okay. Right, x-axis. It goes up to 250. Oh, well, that's going to be 5 again. 5 goes into 250. So that'll be 250. Okay, 200, 150, 150. And again, label it. Time in years. Right, and when you plot it, be as accurate as possible. So, I'm going to do the best I can. Obviously, I've done this by hand, but you've got a grid to help you, and you have to get it accurate to get full marks. So, right, time of 0, activity was 980. Time 0, 980. So, 900 is there, 980 is going to be about there. Okay? Right, 50, 660. So, 600 is there, 700 is there, so 660 is going to be about there. 100, 450, 100, so 500 is there, 450 it's about there. 150, 305, 150, 300 is there, so 305 will be about there. 200, 205, 200 was 200, 205 will be just above it there. 250, 140. So 100 is there, so 140 will be about there. Not bad. Okay. So, right, 4 marks. Accurate crosses, both scales fill at least half of the provided grid, axes labelled with units. Okay. Right, draw the curve of best fit for 1 mark. All right. Okay, let's try not to mess this up. Here we go. Nailed it? Not bad. Okay. Right, use the curve to find the half-life. Show working. It stresses show working, okay? Right. So, to work out half-life from a graph of activity, this is what you do. Okay, that is 980. At that point there. So take that activity and divide by 2, okay? And that gives you 490. And mark that on the y-axis. So 500's there, 490 would be about there, okay? 490. You have to work out what half of the initial activity is, because that will tell you the half-life. The half-life is the time it takes for the activity to drop by half. So, having worked out what half the activity is, take a ruler. I don't have a ruler, but you should use one, and go across and down. So, go across there, and down, and that time there will be the half-life. From there to there is the half-life. And if you've done this accurately, it should be about 90 years. Okay, that's how you do it. And it said show your working. They want to see this across and down line, okay, and the 490 marked. Good. Okay, so the half-life, so T half is 90 years. Right. Plutonium-238 transfers thermal energy as it decays. This energy is used to power heater units in spacecraft. Okay, so you have a bit of a lump of plutonium and it's inside this ceramic thing. Okay, sort of embedded inside a ceramic cylinder. So that's the plutonium-238 and this is ceramic. Okay, so plutonium transfers thermal energy as it decays. This energy is used to power heater units in spacecraft. Plutonium-238 transfers thermal energy at a rate of 0.56 watts per gram. Okay, so we've got 0.56 watts per gram. Okay. Calculate the rate of thermal energy output from a pellet of plutonium-238 with a mass of 2.7 grams. Okay, so we have that pellet there is 2.7 grams. Okay, right, so if you're not sure what to do here, look at the units. Okay, I wrote it like this deliberately because you're told that the pellet has a power output of 0.56 watts per gram. So I write it like that, okay? And if you have a pellet that weighs 2.7 grams, by looking at the unit, you can work out how to get something that is in units of watts, because the question is asking you, calculate the rate of thermal energy output. Rate of energy output, that's power, that's watts, okay? So by looking at the units, you know that if you multiply them, grams on the bottom, grams on the top, they cancel and you're left with just watts, okay? So it's 0.56 times 2.7 watts will give you the answer. And that turns out to be 1.512 watts. Okay, let's neaten that up. 1.5 watts to one decimal place. Okay, right. When plutonium-238 decays, it only emits alpha particles. Explain why a technician can hold a module from the heater safely in their hands. 2 marks. Okay, well, here's the module thing. So this plutonium is emitting alpha particles, okay? But you can pick up this ceramic block thing, this module, safely. The reason is that alpha particles are absorbed by only a single sheet of paper, okay? Alpha particles are not very penetrating. They're easily stopped. Therefore, this whole thickness here of ceramic surrounding the plutonium will easily absorb all the alpha particles before they reach the surface. Okay? Simple. Right. Space probe Cassini was sent to Saturn on a mission that lasted several years. Plutonium-238 was used to generate electricity on Cassini. I can't read my own handwriting. Explain why it was important to use plutonium-238 rather than another isotope with a shorter half-life. 2 marks. Okay. Well, we've worked out that plutonium-238 has a half-life, okay, of 90 years. So that means after 90 years, its activity has dropped by half. So it's heating up this ceramic block even after 90 years. Okay, it's only heating it up half as much, but that's still some energy, okay? So if you chose some other element or isotope that didn't have as long half-life, let's say the half-life was 1 year, okay? It says in the question that the Cassini probe, it took years to reach Saturn. It took many years. So if you had something with a short half-life, it wouldn't be able to generate electricity for the whole mission. You need something that's going to generate electricity for the whole mission. And if the mission is years, you need something with a half-life around at least as long as the mission. So, fairly obvious, right? I hope so. Okay. Well, that's it. So, what can we take from this? Pretty straightforward question, I think. When you plot a graph, you have to get full marks, the x-axis and the y-axis, the scale you choose has to fill at least half of the provided grid, okay? You have to be accurate with your crosses. You have to label the axes, say what they are, and give the unit, okay? You have to know what half-life is. The definition of half-life is the time it takes the activity of a sample to drop by half. You have to know how to work out half-life on a graph. And you have to know that alpha particles are absorbed by 1 sheet of paper, and therefore anything thicker than 1 sheet of paper will easily absorb alpha particles. There we go. Thank you for watching. I hope you found this video helpful. If you did, please click the like button, and it would be a massive help if you could subscribe. It would also be amazing if you could support me on Patreon. All the papers and everything are on my website, drgem.com, and I'm also on social media. Thank you.